Okay, so this is this is beginning of week 9. We're gonna sort of backtrack a little bit. John, I saw you. We're gonna backtrack a little bit, and we are going to how do I say this? We are going to kind of pick pieces of each chapter for one major topic at a time, and then do the next major topic after that. Um, so we're going to start with confidence intervals. It's not really a review. I mean, it's a little bit of a review because I felt that the way it was done before was um, not the greatest. So we're going to do it slightly differently. We're going to start with the concept of a confidence interval and go through all of the different confidence intervals throughout the chapters. The way the book does it is kind of mixing confidence intervals and hypothesis testing, and it's not really the greatest setup in my opinion. So we're going to start with the idea of a confidence interval and then go through all of them. So every confidence interval has the same basic form. This is, it's really it starts in chapter 16 and it kind of runs through 16, 17, 18, 19, 20. It takes a little bit of each. And I'm going to tell you exactly each part that we do, specifically where it comes from. So have no fear about that one. Then we're going to start with chapter 16, which is confidence interval to basics. And we're going to start with basically the idea of a confidence interval, and then go through different specific examples of confidence intervals for different scenarios. So the first one, the idea of a confidence interval is always the same. It's estimate plus or minus the margin of error. Every confidence interval that we do is all estimate plus or minus the margin of error, every single one of them. Okay, every single one of them is estimate plus or minus the margin of error. The estimates are different in how was your, oh, my hands, they're not the greatest, but they're okay. Thank you for asking. I actually, just as a quick side note, I actually went and got my blood tested over the weekend to see what it is. I have not yet heard the results, so I don't have an answer for you in terms of what it is. Yeah, no, I already, I'm not sure yet. Okay, so every confidence interval has the form estimate plus or minus margin of error, every single one of them. Okay, and there's different situations, and I would love to make a flow chart of the different situations. So you say, okay, you first ask yourself, is it this or this? And then depending on the answer, you go, okay, now is it this or this? And then depending on the answer, you go, okay, now is it this or this? And so on. Okay, no problem, Ani. Welcome to the party. In terms of the aloe, not really, but thank you. I have, here it is here. It's this stuff with a little aloe thing, but unfortunately it not really that great, but thank you. Different, feel better. Okay, so Ani's here and Weston is here as well. Okay, so the first thing you want to ask yourself is, are we dealing with means or are we dealing with proportions? So question number 1, does the problem deal with means or proportions? Okay, that's question number 1. Does the problem deal with means or proportions? If it's a mean, we have specific formulas that are associated with it. If it's a proportion, we have various formulas that are associated with it. Question number 2, does the problem deal with one sample or two? As we're going to see, does the problem deal with one sample or two? As we're going to see, sometimes we're interested in probably to share your screen and you type out a document. Yeah, but I want to be able to make a flow chart and kind of do this and then copy it and post it on Canvas. So I'll do it this way, but then you'll see it all. So I can hold it up if you want to copy it over. You can see. No, this is, we're not doing the estimates yet. These are the questions that will. These are first the questions that we're going to be asking for every confidence interval question. One, does it deal with means or proportions? And two, does it deal with one sample or two? And finally, question three, if it deals with means, do we know sigma or not? If it deals with means, do we know sigma or not? Once you answer these questions, then you have exactly the formula. Well, these are the basic questions. Once you answer them, you will have the formula that we need to worry about. There is a fourth question we should ask as well, so I'm sorry. And that is, if it deals with proportions, is the sample small or not? Is the sample small or not? Okay, so these are your four basic questions. And if you want to take a picture of the screen so you can write it down immediately, or if anyone needs me to hold them up, to say so I can give you a couple seconds to copy it. Okay. So now let's do the situation. So situation one, I'm going to go through the book now. So this is in chapter 16. This is in chapter 16. And it is situation one, which is a one sample proportion. A one sample proportion where the sample size is large. Okay, so this is a one sample proportion where the sample size is large. So let's go through the four questions. They should be very straightforward. One sample proportion where the sample size is large. Let's go through the four questions to see what the answers should be. So question one, does the problem deal with means or proportions? Proportions, right? It's a one sample proportion, okay? Does the problem deal with one sample or two? One sample. If it deals with means, do we know sigma or not? Doesn't deal with means. If it deals with proportions, is the sample small or not? Right? It's not small. It's a large sample. Notice that the description clarifies exactly what the situation is. So here's the confidence interval in this case. It is p hat, and I'll hold this up so you know what I'm talking about. P hat plus or minus z star square root p hat 1 minus p hat over n. So write this down. And if we're not sure about any one of these, about what any of these things means, I will explain what they are in a second. But if it's a one sample proportion where the sample size is large, this is the formula that we're going to use for the confidence interval. Okay, so the question is, what is p hat? What is z star? And what is n? There's three symbols that we need to be able to plug into this formula to get the answer. P hat, z star, and n. Somebody give me any one of those. N, the sample size. Okay, so n equals sample size. That part's easy, right? N equals sample size. Now we have p hat and z star. What are those?
The p hat is the sample proportion.
Yes, p hat is the sample proportion, which I'm going to write as x over n, number of successes divided by sample size. Okay, number of successes divided by sample size. Agreed? And what is z star?
It's a number we get from the table C.
It's the number that you get from the tables, correct?
Yeah. Yes.
All right, so z star comes from the table. So in any given problem, what's going to happen is you're going to be given enough information to plug these things in. Okay, and when you plug these three things in, out pops a number here for the sample size for p hat. That's the first part. That's your estimate. P hat. I'll write it. I'll hold it up so you can see what I'm saying. Okay. So this is the formula that is needed for this situation. That's it. You're done. Okay. Now, I should say one proviso. There is one thing that I should add, which is how big a sample size is required for this to be large. So I'm going to write as with a little proviso here. Use this when n times p hat and n times 1 minus p hat are both greater than or equal to 10. Can you see this? Okay, use this when both n times p hat and n times 1 minus p hat are both greater than or equal to 10. That's when you know it's large enough. Can I hold it up again? Sure. Okay. So the next question becomes, and we're going to go through all the situations before we start worrying about actually doing some problems. Because once you see the problems, you'll see how. Yes. So now, question. So now that's the first situation. So the second situation is the one sample proportion, where the sample is small. The one sample proportion where the sample is small. So type that, please. The one sample proportion where the sample is small. So here's what it is. This is in also chapter 15. I think. Yeah, there's also chapter 15. It's going to be the following. P tilde plus or minus z star, the square root, p tilde, and I'll hold this up again, 1 minus p tilde over n plus 4.
Is it chapter 15 or 16?
This is, sorry, 16. This is still 16. So the question is, what is p tilde? What is z star? And what is n? So who can tell me? We're gonna write these things for each one. We're gonna write these things for each one because in general, what's gonna happen is when you're given a problem, you're gonna go right to the correct one and you're not gonna look at the other one. So I wanna make sure that all of our definitions are put for each one. Okay, so someone tell me what one of them is, please. Any one of them. P tilde, Z star, or N. Anyone?
Would the Z star come from the C table and the N be the sample size?
Yeah, okay, those haven't changed, right? So N equals sample size, and Z star comes from the table. Right? Those parts have not changed, correct? Yes? The question is, what is P twiddle or P tilde, depending on, how you pronounce it. I've seen both. I actually pronounce it P twiddle, but people laugh, so I'm going to do P tilde instead. Maybe I'll get less humor. P tilde. It's important to know why it's +4. Not really. It's just important to know when to use it. And in that situation, you just throw in the +4. Okay, but if you're asking why, it's essentially because it gives you a better confidence in them. Okay, you end up with a more accurate one is what it comes down to. So P twiddle or P tilde is the following. It's x plus 2 over n plus 4. Where x is what? I think I'm recording, right? Yeah. Where x is what? Anyone? What is x?
Number of successes.
Number of successes. So you take the number of successes and you add 2, and you take the sample size and you add 4. So you take the number of successes x plus 2 in the numerator, and you take the number of trials, sample size n, and you add 4. So it's x plus 2 over n plus 4. In other words, you take the same p hat that we had before, but instead of using x over n, the number of successes over the number of trials, you add 2 to the successes and you add 4 to the number of trials. And it's important to know when you use this. So star, use when n p hats and n1 minus p hats are not both greater than or equal to 10. In other words, it's not large enough to use the other one, but n is greater than or equal to 10. So you still need 10. Okay, you still need 10. But unlike the last one where np hat and n1 minus p hat each must be greater than or equal to 10, in this case, just n must be greater than or equal to 10. Now, if you have the other conditions, use the other one. The other one is better for that case. Hold it up again.
Professor, do you think you can post this sheet just on Canvas?
I will. I will
Okay.
100%. I 100% will. So those are cases 1 and 2. Those are both from chapter 16. Now, chapter 17 deals only with hypothesis testing. So we're not going to worry about that one right now. And we are going to move on to chapter 18. So chapter 18, if you look at the title of chapter 18, it says comparing two proportions. I wonder which scenario this is. So this is a 2 sample proportions where the samples are large. 2 sample proportions where the samples are large. Okay, and again, we need the estimate and we need the margin. So what if p hat is less than 10? First of all, again, it's not p hat, it's n times p hat and n times 1 minus p hat. And no, both of them must be greater than or equal to 10. If only one of them is, can't do it. Both of them must be greater than or equal to 10. Okay. So the formula is, I'll write it first and then I'll hold it up. And then we can discuss it. See, make sure everyone understands what it says. Hopefully it'll be fairly obvious. First, let me hold it up. Do you all see it? Okay, have you all written it down completely?
No, not yet.
Okay. Good. I hope so. Oh, and I forgot, of course, something. Whoops. What did I forget? Someone tell me what I forget by accident.
Star.
How's Z star, all right? So where does the Z star go?
After the plus and minus.
Yeah, after the plus or minus Z star. So what does everything mean in this example? What does the Z star mean? What does N1, N2, P1 hat, P2 hat? What do these things mean? What do these things mean? N1 equals sample size of first proportion, N2 equals sample size of second proportion, Z star equals table. How about P1 hat and P2 hat? P1 hat and P2 hat? P1 hat equals a sample one proportion, and P2 hat is the sample two proportion. It's pretty obvious, right? In terms of what we've already done, what each of these things means, correct? Are there any questions on any of their definitions? Let's write them down though, just so we have them, because again, you might not do this. You might not look at the other ones when you run to this section. So N1 equals first sample size. N2 equals second sample size. Z star from table comes from table. P1 hat equals X1 over N1. P2 hat equals X2 over N2. And when do you think we use this one? When do you think we use this one? Anyone know? Can anyone take a guess when we use this one? So use when N1 P1 hat, N1 1 minus P1 hats, N2 P2 hats, and N2 1 minus P2 hats are all greater than or equal to 10.
Can you please move the paper a bit?
Oh, I'm sorry. I'm sorry.
Thank you.
Professor, are you going to
Yeah.
post this on the Canvas page?
Yes, I will post it on the Canvas page.
Professor, I think you're covering the part where it says P hat 1 and P hat 2 with your finger.
I'm sorry.
It's okay.
How's that?
That's better.
Okay. You guys have it? You guys have it? Okay. Okay. So now, of course, we have the follow-up. The two sample proportions where the samples are not large. How do we adapt this for the situation where the samples are not large? So it's going to be P1 twiddle minus P2 twiddle, or tilde, plus or minus, what do you think it's going to be? Plus or minus what?
Z star.
Z star times the square root of, and what do you think this part's going to be? What do you think this part's going to be? How do you think we adapt? So the answer is, it's going to be P1 twiddle, 1 minus P1 twiddle, over N1 plus 2, plus P2 twiddle, 1 minus P2 twiddle, over N2 plus 2, like this. In other words, we're still adding 2 to both top and bottom. But, sorry, we're still adding 4 to the bottom. But the difference is that that 4 is split for 2 and 2. Now, the question is, what is P1 twiddle, P2 twiddle, Z star, N1 and N2? We got 5 terms, five factors. What are these 5 all equal to? Somebody give me some of them. There's P1 twiddle, P2 twiddle, Z star, N1 and N2. 3 of them you should get right off the bat. I mean, if you're actually paying attention, 3 of them are straightforward. Which 3 are straightforward?
Z star comes from the table.
Z
and
star comes from the table. Yeah.
And it's the sample size of each, like N1 is sample size of the first proportion, N2 is sample size of the second proportion.
I wouldn't call them the first proportion, but first sample.
Oh, okay.
So the first sample size, N2 equals the second sample size. Z star comes from the table. And then the question is what is P1 twiddle and what is P2 twiddle equal to? In the last case, when we had one sample, we added 2 on top and 4 on the bottom, correct? Right? If you look back. Right? We added 2 on top and 4 on bottom, correct? But here we have 2 samples. So what do you think we do when we have 2 samples? This is for the 2 sample proportion where the samples, better to say, are both not large, because one could be large but not the other. So it's not that they're both small, it's that they're not both large. Okay? And we're going to give the conditions for when to use this one as well. But for now, the question is, how do we define P1 twiddle and P2 twiddle? So what we do here is we add 1 on top and 2 on bottom for both. So here are the formulas. Can you see them? So when do we use this one? So star use when NP1 hats and 1P1 hats and 1 minus P1 hats and 2P2 hats and 1 minus P2 hats are not all greater than or equal to 10. But, so first let's write that part. But
Can you move it more in frame?
sorry,
Thank
sorry, sorry. You see it? Sorry. This is for the two sample, okay, but N1 and N2 are each greater than or equal to 5. But N1 and N2 are each greater than or equal to 5. Okay. At this point, we have 4 situations. We have 1 proportion or 2 proportions for sample size small, sample size large. Okay, are you all with me so far?
Yes.
Okay, so now we move on to chapter 19. 19 starts to deal with the confidence interval for the mean. So this is a 1 sample mean when sigma is known. This is the 1 sample mean when sigma is known. Okay, the 1 sample mean when sigma is known. This one's going to be x bar plus or minus z star sigma over the square root of n. And this is actually in chapter, I thought it was chapter, yeah, this is actually in chapter 20, not chapter 19. 19 doesn't have any confidence intervals. Maybe it does, I don't know. I'm just doing all the confidence intervals. I don't even know what chapter they're in. This is, yeah, this is chapter 20. 19 is called the sampling distribution for a mean. And 20 is called inference about a population mean. So this is really more 20 than 19. Now, what is X bar? What is Z star? What is sigma? And what is N? 4 things that we need to know. X bar, Z star, sigma, and N. What are these 4 things in this case? Anyone? X bar is a sample mean. X bar equals sample mean. Z star comes from the table. Okay, what about N? Sigma is given, right? Sigma is given because you only use this when you know sigma. So sigma is given, and N is the sample size. And we use this one when three conditions are met. Use when the sample is an SRS. What does an SRS stand for?
Simple random sample.
Simple random sample. And the underlying distribution is normal. The third condition is that you know sigma, but I've already included it. So we use when it comes from an SRS and the underlying distribution is normal. If those things all occur, then we get to use it. Next, also in chapter 20, the one sample mean. The one sample mean when sigma is not known. What do you do if you don't know sigma? So one sample mean, but you do not know sigma, what to do? So here's the confidence interval. It's a little bit different, but not so much. It is T. No, it is X bar still. Sorry, X bar still. Plus or minus T star S over the square root of N. So it's X bar plus or minus T star S over the sigma over the square root of N.
Did we already go over T star or?
No, I'm going to do T star in a minute. This is the first time we've ever seen T star. So I will take time to specifically go over what it means and what to do and where it comes from. So first, let's go over what we do know. What do we know about the situation? What do we know about this situation? X bar, T star, S, N. Give me at least one of them or two of them. X bar equals sample mean. What else? N equals a sample size. Okay, excellent. Do we know anything else yet? Do we know T star or S? Do we know what those things are?
Is S standard? No, wait, never mind.
So what are you to say?
Standard deviation.
Of what?
The mean. The mean?
Standard deviation of the mean doesn't make sense.
I
You
don't
can
know.
have the standard deviation of the population, which is sigma, or you can have the standard deviation of the sample.
I'm gonna guess standard deviation of sample.
That's the one. S equals sample standard deviation. S equals the sample. How do you take the sample standard deviation? We know how to do that. We know how to calculate that. We've learned how to calculate that. And of course, Crunch It will do it for us, so we don't have to worry about it. Okay, but what we have so far is the sample standard deviation. And then the question is, what is And then the question is, what is T S? Yeah, I can write the formula down. I'm not sure if that will help much, but that is the formula for it. Yes, no, maybe so. Can you cook on the calculator? On the calculator, what you can do is you can put the data set in the first column of stats and then go to one. Here, I'll show you. So you go to stat and edits. And
the thing we did with like the normal distribution.
yeah, kind of similar. So the first thing you do is you do that, right? You put the stats in, right? The first column, right? Edit stat, that kind of thing. You know how to do that, correct? Yes, no, I need confirmation here. I'm not getting anything.
Yes.
Okay. And then you go to VARs. No, you don't go to VARs. You go to distribution. So you go to set. No, you don't do that either. You go to, okay, go back to stat. I lied. You go back to, why am I not big here? Hold on. Can you all see, am I spotlighted for you guys? Hopefully I am. So you're back here. And this time you go to calc, or so you go to tests. No, you go to calc. I'm all over the place tonight. I'm sorry. You go to calc right there. And the very first one is one var stats, one variable stats. And if you hit one variable stats and you hit a few enters, you get a list of all the data about that one variable stat. For example, you get X bar 3.5. You also get this one right here. The fourth row is SX. SX is the sample standard deviation. If you don't have a calculator, you can just do a Google search for, I mean, I'll show you. I've never done this before, but let's see how hard it's going to be. I'm going to do a YouTube search for, how do I get rid of this? For, here's my YouTube. Okay. I'm going to do it for sample standard deviation. And the very first one, put in the numbers. So let's start over again. Somebody give me numbers. First, it's a sample, right? So instead of population, it's a sample. And give me some numbers to throw in. Someone typed numbers. So let's see what they typed. Oh, okay. So we got some numbers here. We got 4, 34, 5. Oh, I'm not typing them down there. I'm typing them here. 4, 34, 5, 67, and 89. And then I say, then I hit enter your numbers below. The answer is calculated live. Why aren't these? Maybe I got to put commas in between. 4, 34, 5, 67, and 89. And then you go down here and bam, standard deviation 37.7. Literally the first link that I went to was a standard deviation calculator, plug the numbers in, how many numbers, what do they add up to, What's their mean? What's their differences? What are their square differences? What's the sum of the square differences? What's the variance? And finally, what's the standard deviation? Pretty amazing. So the mean is right here, and one standard deviation either direction is here. Very, very cool. And that's a person on a phone. I don't know what that to do with anything, but that was pretty amazing, I thought. The very first link was the answer. Pretty cool. Okay, now, of course, Crunch It can do it for you, as can any Google calculator. And yeah, STDev on Excel works just as well. Every one of these is perfectly fine. These are all wonderful. The question is, what about T-star? So here's the thing about T-star. T-star has its own table. If you go, let's do it again. Let me share, and you'll see what I mean. So if you go to a T-star, so give me a T distribution table. Images for the T distribution table. Go to any one of them. Let's go to this one here. It's nice and big, it looks like. Okay, so here we have a T distribution table. And there's a few things that you should notice right off the bat. Okay, a few things that you should notice right off the bat. One, unlike the Z table where the left side is shaded, in this particular T table, the right side is shaded. So that's one difference between Z and T, is in terms of which side is shaded. Second, the graph looks like what? What does this graph look like?
A normal distribution?
Well, it looks normal, but the fact of the matter is, even though it's impossible to see it, that it's not normal. It's just approximately normal. Essentially what happens is it's a little flatter and a little wider. So if I were to graph a normal distribution, a standard normal distribution looks like this, let's say. This is Z. Then I'm going to graph in a different color. I'm going to graph T. Okay, so I'm going to stop sharing for a second. So where is it? There it is. In blue is my Z, and in red is my T. And essentially what we have is just the fact that it looks kind of normalish. It's just a little flatter and a little shorter. And the reason it's like that, without going into too many complex details, is that the T is merely approximating the normal because we don't have sigma. We don't have the standard deviation. What do we use in place of the standard deviation? We use S. S is an approximation because it comes from the sample. Because of that, the distribution gets a little wider. In other words, our confidence interval is going to be a little bit bigger because of the uncertainty we have that comes from not knowing sigma and having to use S. So T-star numbers are going to be a little bigger than their corresponding Z-star numbers. But how do you get them? You go to the T table. Okay, if I want, for example, a 95% confidence interval, then how much area do I want in the right tail if the middle is 95%? Someone texted and said 2.5% or 0.025. So what I do is I go to the table labeled by 0.025. And when I look at this table, I see lots and lots of numbers. Which one of these do I use? So it's unlike Z. In Z, remember, we have part of the number here and part of the number here. T is a different table. With T, they give you the area to the right. So if it's a 95% confidence interval, I want 2.5%. I look at the 0.025 table, which is right here. And I have all these different possibilities. And the question is which one? To answer which one I use, I look at this column here. This is the DF column. This is the degrees of freedom column. So I'm going to write on this chart here that T star comes from table, and the number of degrees of freedom, the number of degrees of freedom is n minus 1. So if I have, for example, 18 points in my sample, then what do I use for my degree of freedom? If I have 18 in my sample, what's my degree of freedom?
17.
17. So what I would do is I would go back to my thing here and I would look at 17 and I would go, okay, if I want a 95% confidence interval for 18, an 18 sample size, my T star would be 2.110. And that's how the calculators online do it. That's how your calculator in your hand does it. That's how Crunchit does it. That's how any of these websites do it. They get these from tables or they calculated them themselves probably because they're calculators. That's what they do. But that's how you get your T star value. So again, T star, very similar to Z star, comes from a table, but you have to be able to read the table correctly and also know the number of degrees of freedom. Okay, does that make sense? Or more sense? Or any sense? So unlike Z star, T star depends on sample size. Yes, 100%. And the bigger the sample size, what do you think will happen to T star in comparison to Z star as the sample size gets larger? What do you think happens to your T star value as the sample size gets larger? Let's take a look at a Z star. Okay, so this is not the one I want. Images for Z table, let's say Z table. Okay. So, okay, so here we have a table. So let's say we want 2.5% on the right side, right? We already know the answer. For a 95% confidence interval, what's Z star? I don't got to do this. What's Z star for a 95% confidence interval? We already know this one. How much is it? Is one of the three big numbers. It is going to be, someone's texting, they're saying the answer is 1.9, no, 1.645 is for 90%, right? 1.960, that's 95%. So Z star for 95% is 1.960. Let's look at my T table for the same 95% confidence interval, which means 2.5% to the right. If my sample size is 1, which is a very small sample, look how big T star is, because it's really got to compensate significantly for the fact that I don't know sigma. But as the sample size gets larger, then T star gets smaller because I know more. So my uncertainty drops and I get closer and closer and closer, and I keep going lower and lower and lower. Notice here at 40, it just jumps to 50, 60, 70, 80, 90, 100, 1,000. What is it at 1,000? What's it getting closer to as I keep getting a larger and larger and larger sample size? It's a 1.962. Z star is 1.960, right? So what's happening is it starts big and slowly but surely gets closer and closer to 1.960. It approaches a Z. And if I did a 90% confidence interval, which has 5% on the wing. It starts at 6, and I go down, and what do I get closer and closer to? 1.645, which we know is the Z value. And in fact, look at these guys. We have 1.645, we have 1.960, and we have 2.576. Those are all the Z values for 90%, 95%, and 99%. But what you'll notice here is it also has a lot of other ones. So if I said like 99, I don't know, if I said something like 80%, an 80% confidence interval, and you're like, oh my God, we've never done 80% confidence interval. Well, wait a second, 80% confidence interval means how much is in the wing? What percent's in the wing? Yes, the sample size, so yeah, 10%, right? So we go to 10%, we go down, and we see that we get 1.282, right? My Z is 1.282. And at 1,000, my T star is already very, very close to it. So close that they approximate to the same thing, right? So yeah, so the sample size gets larger, T star gets smaller, and gets closer and closer to Z star. So T star is a value that we use when we are when we don't know sigma, so we can't use Z star. So we use kind of like the next best thing. That's essentially what it comes down to. Okay, and the question is, when do we use this? So use when the sample comes from an SRS and N is greater than or equal to 15 if there are no outliers and the population distribution is moderately skewed, and N greater than or equal to 40 if there are no outliers and the population is strongly skewed. I'm going to hold that up so you guys can see it. So these are the conditions. You guys all have it? Yes, no, maybe so? I hope so. Oh, no, you don't have it? Okay. Is it good? Yes, nobody? Okay, good. Now, as we saw with the applet like 2-3 weeks ago, by n equals 30, even strongly skewed distributions look very normal. So this is kind of a safe number, n greater than or equal to 40. It's saying, okay, if it's really strongly skewed, make sure n is 40 or more. If it's moderately skewed, make sure n is 15 or more. If it's already normal, then it makes no difference because it's already going to be normal. But these are kind of arbitrary safeguards to make sure that the central limit theorem holds. Okay, so that is our next example. So we have 1, 2, 3, 4, 5, 6 done. We have 2 more to go, and then we'll be done with confidence intervals. So the next one, can anyone guess what the next one is? Anyone? Huh?
Chapter 22.
Yeah, we're going to compare 2 means, right? So the next one is going to be 2 sample means. This, by the way, is chapter 21. 2 sample means when sigma 1 and sigma 2 are known. So this is 2 sample means when sigma 1 and sigma 2 are known. So, anyone want to take a guess as to what it's going to look like? It's going to be x1 bar minus x2 bar plus or minus z star square root like just like that. You want to write that down. Does that seem reasonable based upon the 1 sample case? Yeah, does that seem reasonable? It's kind of very similar. Let's go through it. There's 1, 2, 3, 4, 5, 6, 7 numbers here. What are the 7 numbers in this case? What are the 7 values? What do you guys think? The 7 values. Anyone? Anyone here? Let's do a quick roll call. If you're here, just put the word here in chat. And I'll look at this later and see who's not here. So, can someone tell me any of the 7 terms in the
Z
formula? Huh?
stars from the table. X1 is the sample mean of the first sample. X bar sec2 is the sample mean of the second sample. And then sigma 1 squared is the standard deviation of the first sample. Sigma squared 2 is the deviation is given in the second sample, and then n1 and 2 is the sample size of each thing.
I got nothing to say. That was perfect. That was perfect. That was amazing. First sample size and 2 equals second sample size. Sigma 1 equals first population standard deviation. And sigma 2 equals second population standard deviation. And when do you use this one? When do you think you use this confidence interval? So use when both samples come from an SRS. So they have to come from an SRS. So both samples come from an SRS. The samples are independent. One does not affect the other. The samples are independent. They are normally, they come from normal distributions. They come from normal distributions. Okay. Or if not normal, then if N1, I'll hold this up in a second, I'm just saying it, but if N1 plus N2 greater than or equal to 15 can use for moderate skewness with no outliers. And if N1 plus N2 greater than or equal to 40 can use with no outliers and strong skewness. Of course, I will be posting these. Okay, but I will give you a few minutes to write them. Hopefully you can see them.
Can you move it more in the camera? Yeah.
Is that better? that good?
Yes.
Okay. So that is the 2 sample mean when sigma 1 and sigma 2 are known. So what do you think the last of the 8 is going to be? 1 to go. We're so close to the end. What do you think the last one's going to be? When sigma is not known. So 2 sample means when sigma 1 and sigma 2 are not known. So notice, remember those 4 questions that we asked in the beginning? Those 4 questions that we asked in the beginning tell you which of these 8 scenarios is appropriate for that specific problem. So you have 8 confidence interval situations. You just say, okay, it's not this, it's not this, oh, it is this, and so on, right? You just pick the right one. So what do you think this one's going to be? Can anyone take a guess as to what this one's going to be?
It's gonna be the same equation as the first one, but instead of z star is t star, and instead of sigma squared, it's gonna be s squared.
Love it. Did you all get that? X1 bar minus X2 bar plus or minus T star squared of S1 squared over N1 plus S2 squared over N2. There is a nuance about this one. But before we get into that, let's just make sure we understand each of these terms. Someone tell me what these terms represent, please. Anyone? What do these terms represent?
X bar 1, X bar 2 is the sample mean of t stars over t stars over s squared is the sample standard deviation, and n is the substitution.
Wonderful, wonderful, wonderful. Again, I'm not even going to write them out because I'm too lazy and we're running out of time, but you can write them out. So the question is, when do we use it? Well, first of all, there is one situation. If you recall, the one that we did with the degrees of freedom, we did say that T star comes from a table and the number of degrees of freedom So what was the number of degrees of freedom for the example that we did when we had 1 sample? It was n minus 1. But here we have 2 samples. So what do we do? So the answer is there's the easy formula and the hard formula. The easy formula is what you use when you don't want to do any major calculations. So number of degrees of freedom is the smaller of n1 minus 1 and n2 minus 1. So let's say 1 sample is 10 and 1 sample is 13. What will be the degrees of freedom? One sample's 10, 1 sample's 13. What's the degrees of freedom?
Would it be 9?
It will be 9. It's the smaller of the two. Or for more accuracy, it's the following, which is a complicated formula that you will not be expected to memorize or even use, but you should know it exists. And I'm going to write it down. Because when you do things on a calculator, the calculator doesn't care how complicated formulas are, because the calculator just computes. So it doesn't understand that no one in their right mind would want to use this. But technically, this is the formula for the number of degrees of freedom. Very oof is right. Very complicated looking. But if you're going to use Crunch It or a calculator online or something like that, this is a formula that they're going to use. So what I'm going to do is I'm going to fill these out tonight, write them out when I have time, and then I will post them all on Canvas. And I will move all of the videos from Zoom and the ones that I currently have onto YouTube. I will post the YouTube link on the Canvas homepage, so you guys can go directly to it and you can watch all the videos, especially this one with its formulas. And what we will do next time is we will finish up confidence intervals and do a bunch of examples. So this week is confidence interval week. Okay, just all confidence intervals all week long with lots of examples. Can you play the smaller? Yeah, just calculate n1 minus 1 and n2 minus 1 and pick the smaller one. If one's 10 and one's 13, if one sample is 10 and one sample is 13, it's just, okay, 9 and 12, 9 smaller, 9, done. But if you want more accuracy, use this formula here. Okay, so this is confidence interval week. Next week will be hypothesis testing week, and we'll almost be done at that point. I don't like how the book does it with lots of a little here, a little there, a little there. I like doing all confidence intervals, all hypothesis testing, finishing up all the other stuff that we skip, and going from there. Okay, so yeah, I like this better because you focus on one topic. I already extended all the homework, by the way. Every homework is I went on Launchpad. Every homework I gave at least 2 more weeks, from section 1 all the way through chapter whatever. They are all extended. And just so you know, I'm going to put up lots of homeworks over the next few days, because we did a little bit of this chapter, a little bit of this chapter, a little bit of this chapter. When you open those homeworks, you'll be able to do some of them, but not some of them, because you haven't learned the other stuff yet. So what I would recommend is doing the confidence interval stuff of each chapter and not doing the rest. And then when we cover hypothesis testing, do the hypothesis testing stuff of each chapter and then leave the rest. And then when I cover the rest, then do the rest. Okay? We didn't see the menu today. I know. He's slacking. I mean, he should have come out, what, a half an hour ago? Dad? Come out here. They want to know what's for dinner. You can tell them if you'd like.
Lobster biscuit.
No, seriously, go make me dinner.
Go. Your dinner.
So,
okay.
no, I want dinner. Then okay, where you going?
I'm going to get my phone.
Okay, fine. So, so anyways, I don't even know what lobster. I'm Jewish. Do you think I eat lobster? How do I know what that is? Anyways, all right, guys, we will end here, and I'm just kidding. You can do whatever you like, but yeah, get me food.
I'm going to give you a cinnamon on the Bergerac dinner.
Whatever. Just
3
go.
grapes.
I'm not. Anyways, don't die. I'm the one who's dying, not you. Jeez.
No, you're not.
We'll see about that.
Actually, it should be better. Is it better, your hands?
They haven't acted up today. I'm really happy about that. Maybe the medicine's working. We'll see.
Okay.
We'll see. Or maybe it's the the gel that
Well,
Giovanni
whatever it is, I
recommended.
mean, you just keep doing it until it goes away.
Yeah, that's the plan. So yeah, okay, good times. All right, everyone. I'll have the food review next time. I'm gonna stop. I'm gonna stop